speaker probably needs no introduction by me. It's Professor Gabor Somorajai, who's going to talk about his recent work on the fabrication and characterization of platinum and silver nanoclusters using electron beam lithography.
Thank you very much. Over the last several years, I've been working in two areas of catalysis science, and I need to use the slides and the remote control. The one area is what I call high-pressure surface science. That is, in these days, there is a proliferation of techniques that are available to look at the surface while the catalyst is working on a molecular level. Many of these techniques are old, such as isotope exchange or infrared spectroscopy, but many of them are new. Clearly, NMR is now become possible to do in a reactor. I'm practicing some frequency generation surface vibrational spectroscopy, which has advantages as well as disadvantages over infrared spectroscopy. And in situ scanning tunneling microscope, that is, I built a tunneling microscope into a catalytic reactor and scan the surface while the reaction is going on. So this is one area. Just show you some of these. This is a scanning tunneling microscope, and this is a reactor cell. And then with a transfer rod, we can move the sample from the vacuum where the sample is characterized into this cell. We close the gate valve, and then we run the reaction, and then look at what's happening on the surface with the STM. The other technique is the some frequency generation, where we use two laser beams, a visible and an infrared beams, and sum it up, and the sum frequency is in the blue. And then by tuning the infrared, we can actually get a vibrational spectrum in the blue. Now, to see the second order effect, you have to meet two selection rules simultaneously. Both the dipole, the infrared selection rule, and the Raman, the polarizability selection rule. And this is met only at the surface that has no inversion symmetry. So the bulk doesn't contribute to the signal, the gas doesn't contribute to the signal. So if you see a signal at all, it's a surface signal. And so compared to infrared spectroscopy, where you have to subtract all those things that are not contributions other than the surface, here there is nothing to subtract. The signal to noise is much better. That's the advantage. The disadvantage is that you need a fairly flat surface, optically flat surface, so the laser beam don't scatter all over the place, and that is not a necessity in infrared or Raman spectroscopy. Now, what we find when we use these techniques at high pressures are rather profound. This is carbon monoxide. This is some frequency vibration spectrum of carbon monoxide on platinum 111 at low pressures. The 1 torr now is low pressure for me. You see, the top side, and this is the gray side here. But by the time you go to 150 torr, you remember Wolfgang Sachler was mentioning about platinum mobility. Well, you see an entirely different vibrational spectrum. And this is due to, this right here is platinum carbonyl, PPCO4. And this is an incommensurate lattice of carbon monoxide, this tail here. And on the scanning tunneling microscope, which was taken at the same pressures here, you see that by 1 torr, all the steps that are very nice and smooth at low pressures are becoming very rough. And by 150 torr, you see this incommensurate ordering of CO on the surface. And by the time you go to an atmosphere, all you see are these platinum carbonyl units, and you can twist them all over the place with the platinum, with the STM tip. The surface becomes very mobile. Now, platinum, it turns out that this is reversible. When you reduce the pressure, you go back to where you started from, but in other surfaces like rhodium, it is not reversible. So the picture one gets from STM that as you increase the pressure, the surface becomes highly mobile. This is a some frequency generation spectra of during CO oxidation. These are turnover rates to a platinum site. So this is a reaction which is very, very rapid at these temperatures. You see the temperatures are right here. This is below ignition. At this particular oxygen to CO ratio, the ignition is above this temperature. So below ignition, all we see on the surface are topside CO, which is not a reaction intermediate. The reaction rate is inversely proportional to these, to the topside CO. Now, what is the reaction intermediate? We don't know. We don't see anything else by vibrational spectroscopy. Our time resolution here is rather poor. We need about 25, 30 seconds to scan a spectrum like that. Above ignition, however, we see an entirely different spectrum that can be assigned to various CO species, including these carbonyl species, all of which seem to be reaction intermediate because the reaction rate is proportional to their concentration. So in this circumstance, we see reaction intermediate. At below ignition, we do not. But at least we can distinguish between spectator species and others. Then we look at propylene hydrogenation, and again we see species that are only present at these high pressures. We never see them in ultra-high vacuum. And these are the species that turn over. This is 5-bonded propylene, and this is 2-propylene intermediates. Let's see if I can focus this. No, I cannot. But there are other intermediates like these propylidines, which are very stable even at low pressures, which are clearly spectators during the reaction. The picture that emerges is that everything we see at low pressures seem to be spectators because they are too strongly bound to turn over. And the species that turn over get on the surface after all the strongly absorbing sites absorb things, and they turn over. But we see those only at high pressures because they are so weakly bound that when you depressurize, you evacuate, they go away. And this is, for example, the fate of this 5-bonded propylene or the 2-propylene intermediate. So there's a lot of learning when you go to high pressure. And so we even have a mechanism now for these light olefin hydrogenation, and we did also cyclohexene hydrogenation, dehydrogenation. And what you usually find that even though you run hydrogenation, the surface is full of stagnant, dehydrogenated species. On platinum, for example, we see cyclohexadienes, 1,3 and 1,4, present on the surface while we are hydrogenating. So the situation is rather complicated. The surface is full of strongly bound species that don't really want to turn over or not sure that they turn over, and then weakly absorbed species that do turn over. So I really think that looking at the surface while it's working is a good way to go. But this is not what I want to talk about, but the other area that I'm focusing on the last 5 years or so. And this is to try to have more control over catalyst preparation. And so I'm using this electron beam lithography to deposit nanoclusters of metals, and I'm focusing on platinum and silver. And the co-workers I have who are also listed in this talk are Aaron Eppner, who's a graduate student focusing on platinum clusters, and Armen Avoyan, who's a postdoctoral fellow focusing on silver clusters. And their work is what I'm going to talk about. Now, clearly, catalysts are nanoscale materials. One of the oldest, if not the oldest, nanoscale technology actually is vying for being first with photography, 1823, 1837 vintage. But there are many modern technologies which also use small particles. Small particles. Now, this area of research that is outside catalysis, but involves nanoclusters, when it becomes technology, grows now at a rate of about 20 to 40% a year. One technology is the microelectronics technology. The other one is the disk drive technology, where one has to have control on the 100 angstrom spatial scale to build the next generation of devices. And my hope is that if we establish such an atomic level or nanoscale control on building our catalysts, catalyst-based technologies will catch up in terms of growth rates with all these other technologies where the material science is controlled on the nanoscale much, much better than in the field of catalytic technologies. This is one of them. Intel is clearly selling these transistors on a Pentium 2 chip. There are 9 million transistors. The next generation, Pentium 3, will have 13 million transistors in an area of 2 centimeter by 2 centimeter. Now the technology controls the space. The spatial control is of the order of, it says 2500 angstrom, but in fact the control is down to an 800 angstrom level. Okay? Now it is not just the size that is crucial in making faster devices, but the interconnections. And of course, to build 13 million of these things in a 2 by 2 square centimeter area, you also have to pack them in 3 dimensions. And that has been very well solved. Now, this technology has a lot to offer to catalysis, in my opinion. Now, the way we synthesize catalysts is, of course, the sol gel methodology, ever since Mitash in 1923. And so we have salt solution, reduce, oxidize, we make particles like this with a certain particle size distribution as well as spatial distribution. Both of them are poorly controlled. Typical electron microscope of platinum on gamma lumina, and it shows the little black dots, and clearly the spatial control and the size control is not what it should be when you compare it with other nanotechnologies. So I am blaming selectivity problems and deactivation problems with our lack of control. Now this is not always the case, but I really hope that if we have both the structure and the distribution of these particles under better control, we can do better. And as I see in the future, mostly because of environmental concerns, we will be pushed toward 100% selectivity and very long life. And I am claiming that we have to change our fabrication techniques in order to get there. So there are many attempts, and I'm going to show you some of them, but if I focus on my own. And what I'd like to do is to have molecular control over the size, location, structure, and the promoter distribution on these transition metal catalysts. So what do we do? Now I borrow a page out of the microelectronics fabrication technology, and this is, but instead of using photolithography, which is right now the norm in the technology, I use electron beam lithography. And I'll tell you the reason why. We take an electron beam, and the technology is that you take a silicon single crystal substrate, which is oxidized. Then onto that, one spin coats PMMA, polymethyl methacrylate resin, polymer. Then the electron beam allowed to impinge on it to decompose the polymer. And the size of the decomposition area depends on the size of the electron beam. So the electron beam comes in and it decomposes the polymer. Now then using propanol, isopropanol or other solvent, one removes the decomposed polymer. Then you evaporate a metal film everywhere. Then you peel off the metal film and the polymer right here, and you're left with the metal film right here in the holes, and this is what you get. Now, the reason why I do electron beam lithography because in photolithography, if you use an excimer laser, you are at a spatial resolution of about 1,000 angstroms. Well, by catalytic standard, that's enormous. Okay, so what we need, there is an electron beam that we have now in Berkeley. It's called a nanowriter, which gives you an electron beam size of 2.5 nanometer. That's 25 angstroms. So in fact, I can punch holes and make metal particles of the size of 25 angstroms or larger. Okay? Now that is overlapping most of the catalytically important particle size regime. So that's why I use this electron beam lithography. Now, so this is the result. This is now platinum on oxidized silicon. And these particles are all this, an electron micrograph picture of these things. In this case, the particles are 500 angstrom in size, distances are 2,000 angstrom. It's a very nice pattern. You can control, you can dial in the pattern and put these things down in any shape or form you wish. So this is a typical area like that. Now, as you well know, in order to have a signal, a rate, a catalytic reaction rate out of a sample like that, I have to do two things. One, to clean off the junk, the carbon coating that is all covering up the metal, so you expose the true transition metal. The second one is that you have to have enough area, surface area, to see a chemical signal. So we need an area of about half a square centimeter, full of these little dots, about 10 to the 11 of them. It takes about 24 to 30 hours to make these things, make these patterns, because unlike in photolithography, we cannot go parallel. We have to go in series, like a machine gun. You make these little holes there. And so that takes about 30 hours. Now, the advantage we have over microelectronics that we don't need ohmic contacts. We don't have to make conducting wires here. All we want is surface chemistry, you see. And so that's a big advantage in the fabrication of these sections. Now, then by thinning the back of the silicon wafer, one can do transmission electron microscopy on a single particle like that. And this is the electron micrograph. The particle is polycrystalline, but it has 1-1-1 orientation surfaces. And so from this pattern, both from the bright and the dark field, one can get a structure on each of these particles. The two techniques that can characterize single particles is atomic force microscopy and transmission electron microscopy. Okay. Now, this is the atomic force microscope picture of that same sample that I showed as an electron microscope picture. Here the heights clearly indicate that we have been successful on, these are about 100 angstrom in size, little hills, and in between you have these oxidized silicon species. They're very nicely ordered and beautiful. Now, how do I clean them? Well, we found after all sorts of trial and error is that about 400 electron volt neon beams sputter off all the carbon. It also sputters the platinum and the silicon, but very gently. So we lose very little of the height, but we can clean up the sample such that we get a carbon-free transition metal surface. Now, so we started to first look at the thermal stability of these things. So you take it and heat it in vacuum, but electron microscope vacuum is not that great, but good enough. And so you see the particles here before heating and after heating. Before heating, this is the bright field images. You see polycrystallinity here. And here you hardly see any polycrystallinity. Well, the first thing we find is that we grow one big single crystal with 1-1-1 orientation when we heat it in vacuum. This is platinum on oxidized silicon. Now, when we heat it in 1 atmosphere of hydrogen, and then we look at the picture again, the same thing. We seem to recrystallize the platinum surfaces, so they are almost single crystalline, and again the 1-1-1 orientation dominates. Okay? You see all these changes of shade indicates polycrystallinity, which is disappearing when we heat in hydrogen. Now you heat it in oxygen. Well, in this case, we see some distortion of these samples they become more polycrystalline, probably roughened up. I don't quite understand what we're seeing here, but we do not see any major migration of platinum onto here. This is 700 K, so it's not that high, but it's certainly 1 atmosphere of oxygen. So platinum is very stable. As you will see, silver is much less stable under these conditions. So this is just to show you that the platinum particles are not spreading out. These nanoparticles love to stay like this. And the reason for it, I'm sure, is the same reason why these first catalysts are stable, is surface energy. Is that the metal surface energies are very high, and so it doesn't want to spread. If anything, you will see the oxide will spread over the metal and not the other way around. Okay, so in these cases, these are very stable systems. With no heating, and after heating, you don't see much change. There's a bit of more movement, but when things are moving, I think the whole particle seems to be moving, and very little other things happen in between. Now, then you take atomic force microscopy. These are the particles, platinum particles, and we go over them to image them with a 15 nanonewton force. There is a part, AFM instrument, that you can do that routinely. Okay, so you go over the force and that images these particles. Now when we increase the force to 20 nanonewtons, we start to break the particles. We break off the particles. And just to show you that I'm right, this is the area where we use 20 nanonewton force. And you see that the particles are gone. But outside, where we were just imaging with a 50 nanonewton force, the particles are still there. So at least I know how mechanically I can break these particles one by one. Okay? Now, so you take these particles, we take these particles now and put a high pressure cell over it and run catalytic reactions on it. Well, the first thing we have to do is to measure the metal area that is exposed by temperature programmed desorption. So this is now the polycrystalline foil. This is our standard reference state. And this is now from this nanocluster platinum array that was neon ion bombard clean, a TPD of deuterium, and a TPD of carbon monoxide. In both cases, we use isotopes because the background is high, so you just to distinguish between the background and the signal. And what we see is already interesting. CO has a signal which is about 1/4 of that what we get for deuterium. Now the only explanation I can give for that is spillover. Is that in this case the deuterium spills over from the platinum to the oxide because the oxide to metal area ratio is 4:1. It looks like that in fact the hydrogen goes over maybe forming OH groups or whatnot, but at least this signal is 4 times as big as this one, and CO does not spill over. So I'm looking at this as titration of the surface area of the platinum clusters. Now then, first we did ethylene hydrogenation, because in those days, when we first thought that I didn't dare to heat these clusters, I was afraid I'm going to lose them. It cost me about $1,000 per sample, okay, to get one of these things. And this is my agreement with the people who run the nanowriters. The nanowriter we got in Berkeley not because of catalysis, but because this was the only way to make zone plates for the synchrotrons of the world. These are zone plates that are used to diffract X-rays coming out of synchrotron radiation. These are 18-inch plates. And so this whole nanowriter was developed to make these huge plates of silicon gratings for diffraction. And once you can make an 18-inch plate, you can certainly make a 1 square centimeter for catalytic purposes. And so this is why the technology is now available. But in fact, we can do ethylene hydrogenation and we can get turnovers at room temperature, which is roughly equal to what we get on a dispersed platinum particle on the platinum catalyst or silicon under the same conditions or on a single crystal. We then did butene isomerization. This is a typical turnover number samples and sputtered, this is sputtered platinum 111, and so from these we can get rates, and what you see here, you get some selectivity here toward cis-2-butene. Cis-2-butene is more than trans, and thermodynamically just the opposite. This is more stable. I don't know what to make of this, but what we are after is selectivity. My hope is that as we change the particle size, change the distances between particles, we can get some interesting selectivity patterns for the future, but we haven't got that far yet. Now, silver. As you well know, silver for ethylene oxidation is used on alumina, on alpha alumina, for good reason. And so the challenge was, how on earth do you put silver on alpha alumina in this case? So what we do here is this. We start with a silicon wafer. Then this is a long slide. The first one is an alumina is deposited by sputter deposition. If you just raise it or lower it, that's it. See, we deposit by ion beam assisted deposition an alumina layer on the silicon wafer. Now this was a bit tricky because we needed to get a rather smooth surface of alumina, and that wasn't that easy, but I think we succeeded. Then you put the photoresist, and then you do the same electron beam exposure, development, silver deposition, lift off, and you end up with silver clusters like that on the alumina. Now this is how it looks like. It's not as beautiful as the platinum clusters, and I blame our lack of control of the alumina. The alumina is rough, and when there's a roughness, then of course the silver particles are not lined up very nicely like they lined up on platinum or silicon. But we in fact get a very nice silver cluster array here, and this is the atomic force microscope image of how these things look like. There is more defects in there than in the other one, but not too bad. So now we start to characterize again thermal stability. These are the AFM images of silver clusters. When they're heated in air at 300 centigrade, they evaporate. You can clearly see them going away. We have no evidence of silver diffusion along the surface, but we definitely have evidence of evaporation. Now, we can do Auger spectroscopy on these particles before heating and after heating. And when you do sort of Auger, this is not Auger spectroscopy, it's Auger microscopy. We can focus down on a 500 angstrom square area with an Auger beam, and what we see is that these are the two areas. This is the silicon, this is the silver. So on the silver area, the red, you see silver. On the silicon area, you see, this is the silicon area, you see silicon and oxygen. Just what you want to see. Now, you heat it, and look what you see. On the silver particle, you see silver. But you also see oxygen, and you also see silicon. And on the silicon part here, all you see is silicon. That is to say, the silver stays put, but the silicon oxide migrates over the silver. And so what you get is probably silver silicate, and this is precisely why the catalytic technology didn't use silicon as a support for silver ethylene oxidation, but uses alumina. So what does alumina do? Well, when you do the same thing on silver clusters, deposited aluminum oxide, sure enough, there is no sign of any migration of aluminum onto the silver in this circumstance. And so it is clear that the silver alumina system under these conditions, which is not too far from the ethylene oxidation temperature, in fact very stable. But the silver silica system is not. Now, so the question is, how can you make a mass technology out of this? Okay? Well, there is one way that one might work, and this was originally suggested, and it seems to work, in 1996. And this is what's called imprint lithography. You take one of these samples that is prepared and press it in like a stamp, press it into a viscoelastic polymer. Now what happens, the polymer carries now the imprint of this rough surface, and then you can go through etching, reactive ion etching, and in fact can come up with the image of what you impressed into that polymer. And it seems that this type of etching maintains maintains the fidelity of the distances above 500 angstroms, because that's all these people have done. Okay? So I really think there is an opportunity here to make this faster by the stamping method, or duplicate or multiply these samples once you made a master of some sort. Okay? And we are working on it. We're trying to see if this is really working with the fascinating surface chemistry. Okay. Now, of course, you can play games here because you have control. You can put platinum here, palladium here, copper here, in any configuration you wish. Okay. Now, it is my hope, because I don't understand selectivity at all, and I understand activity much more, is that the selectivity in catalysis is due to secondary processes that are diffusion controlled. So if this is the case, then if I change the distances between these particles, it may change selectivities. So this is one of the things that we are trying to look for and go for. The other one is, of course, this will never give you a few hundred square meter per gram type of surface area that you need in technology. In order to get there, you have to three-dimensionalize this process. Well, that's a challenge, but in fact, the microelectronics industry is already building three-dimensional microelectronic circuits. Of course, they don't have micropores in them to get the molecules in and out, but they have contacts, a very intricate contacts with their ohmic contacts. So there are, in fact, all sorts of technologies already trying to make three-dimensional circuits. One of them is that you actually build channels and then etch these channels parallel here. So there's a metal like aluminum, gold array, and then you etch out the aluminum and keep the gold in there, etc. So there are all sorts of interconnect etching, three-dimensional interconnects for ohmic contacts are being made. And some of these technologies, in fact, are in the nanoscale. Not zeolite-like sizes, but 100 to 200 angstroms sizes are being etched in three-dimensional these days. So anyhow, this is a challenge. I haven't touched this, and I don't plan to, for a while. We have enough problems as is to stay two-dimensional. But clearly, this is a way of building a high surface area catalyst, if you wish. Now, there are other techniques. The other people try to do these things, and I'd like to call this to your attention. One of them was a shell effort in Amsterdam, where they were doing spin coating of salts and then evaporating and then growing particles, and the particle size distribution was quite narrow. I don't think it was narrow enough, but certainly was good at that. The problem is that with this type of deposition, they don't control nucleation. So there is no ordering possible here. You get the nucleation sites without much control. But this was a way of doing it. Also, laser deposition was used to deposit nanoparticles in these days. Also, I'd like to call your attention to Professor Safner's efforts of doing some very nice placing of various metal particles, like the previous talk indicated, into zeolite cavities, and trying to anchor them such that during the reaction these particles would not come out. Well, I wish them good luck, as I feel these are one of the approaches, and it might work better than what I suggest, but it is yet to be seen. So the final other preparation is this sol gel technology, mycel technology, where they make nanocrystals of semiconductors, and Schmidt in Germany, he deposits beautiful metal clusters, which are really a delta function particle size distribution. And the problem is that, of course, that these clusters are stable with an organic coating around it. Now, how on earth are you going to take out the organic coating and start to do catalysis with these is a real challenge. But in fact, these particles can be made. So as I see everything that drives us in the future indicates that there is a need for high technology catalysts where the fabrication is under better control than what we presently practice in this field. I think that for structure-sensitive reactions, there is a possibility this way to develop unique catalysts. And clearly, I mean, this is a CONO is a structure-sensitive reaction, and of course, ammonia synthesis is a structure-sensitive reaction. And the other interesting aspect of this, and this is my final point, is the oxide-metal interface catalysis. As you know, Alex Bell and I have for years tried to develop the science of the active sites, which is the oxide-metal interface, and we have plenty of evidence by putting little oxide deposits on metals that in fact the activity of these oxide-metal interfaces of certain non-reducible oxides is much greater than that of rhodium, for example, for hydrogenation of CO2, and we blame these Lewis acid sites that form at these interfaces. Now, with such a fabrication, if you make the catalyst, metal catalysts as mountains, or you make them in a ditch, you see, you can control the oxide-metal interface area in a very nice way without changing, let's say, the metal particle size. So there's a lot of control you can have to fabricate these catalysts as you wish, okay, for the future. And so this is my conclusion. You can actually deposit on substrate and use them as model catalysts. This research, as most of my work, has always been funded by the Department of Energy in the material science area. And Union Carbide funds the silver cluster work in my laboratory. Thank you very much.
We have time for one question, perhaps.
The ability to make these preparations depends on maintaining the integrity of these little clusters. One does not move over and collapse to the next one. But this morning we were talking about how labeled platinum is, carrying hydrogen would explain hydrogen spillover. There seems to be a contradiction there I don't understand. Perhaps you can elucidate a little bit.
This is one of the interesting answers that could come out from studies of these particles. Okay? We obviously have a way of measuring if the platinum spreads. Okay? We will be able to do that chemically. We will be able to do that by AFM, well, not AFM, but electron microscopy, because the density, electron density of platinum is so high that you should be able to see it wherever it is. I think that these are the samples that will give an answer. Probably in some cases, these particle areas will not be stable. In other cases, they will be very stable. And I don't have any answer, but this is one of the, I was very interested in what Wolfgang had to say, because obviously the spillover situation is one that has been around for so long, and well, we'll find out how far it goes.
You showed that some of these particles maintain their integrity in the spatial arrays, essentially the 1,000 you see.
700K we went to, 700K in oxygen, in platinum, and we saw no sign of spreading. Now after this oxidation, we reduced them, but they should have spread by then. Okay, but we didn't see any spreading. It may be the oxide metal interface is crucial. Maybe something else. I mean, this is the...
Just a comment, we put the platinum in solid gel in small pores and it doesn't move. It stays there. We put it on the surface of a impregnated catalyst and it squirts all over.
What I love in this is that you can now deposit not just alumina, but we can put down titanium oxide. Okay? We can sputter alumina such that it stays gamma alumina instead of sputtering alpha alumina. Okay? The recipes now how to do that. Okay? So there is a possibility not just to control the metal, but the oxide as well.
Thank you very much again. It was most interesting.